Hello students, welcome back. I'm not so sure whether section 4 should go to lesson 2 or lesson 3, or maybe it should become an optional section. I don't know, let's just cover it. Here's a review of some properties of GCD, which I'm going to leave to you. The proof is a bit tedious, but not too bad. So commutativity, the GCD of A, B, and GCD of BA, they are the same. And of course, the proof for that is pretty obvious because, here we have commutativity, so no problem there. As for the associativity, it's going to be a bit trickier, but if you utilize this linear combination, then you should be able to prove the associativity too. A bit tedious, yes. And this distributivity, that's going to be not as bad as associativity in terms of tediousness, but still a bit of a work. And the other two, these are trivial. They're all left to you as homework problems. Or maybe not even that. Too tedious for homeworks. Alright, these are some properties of GCDs. Now let's start from there and extend those to GCDs of more than 2 integers. Using the associativity, we can define the GCD of 3 integers ABC as the GCD of A of GCD of BC. You see, we have too many GCDs there. In this kind of case, just using parentheses is going to be simple enough. And then if you have n integers, you can define like this inductively or recursively. And then GCD is, let's see, we have 3 ingredients, right? Greater than or equal to 0. Let's see. I missed that. D has to be greater than or equal to 0. So that should be condition number 1. So this is not completely right. D is greater than or equal to 0. That's number 1. And then D divides all AIs, A1, A2, A3, and so on. Or let me just use for all as this renders notation. Oh, okay, all right. Let me rewrite. Okay, that's number 1. Okay, all right. Talking and writing at the same time is often difficult to do. So non-negative, that's number 1. Number 2, common divisor. And then number 3, linear combination. Let's use the same color coding. Greater than or equal to 0, a whole number, green, common divisor, blue, and linear combination, red. So we need these three. And here I neglected the green one. Maybe I thought it was just trivial. Sorry about that. And as for the proof, yeah, I don't think that's really worthy of class time. You can do it inductively or recursively. And then when the GCD is 1, we say these are relatively prime. But the GCD of n integers is 1 does not mean each pair is relatively prime. If each pair is relatively prime, then necessarily that GCD of everything is 1, but not vice versa. You see, the converse is not true. For example, if you have GCD of, let's see, 2, 4, 10, and 16, they're all even numbers, so they cannot be relatively prime, okay? But the last one here, let me select like this and find out GCD, and GCD will be 1. So the GCD of these 5 numbers is 1, but pairwise, they are not relatively prime. 16 and 7, yeah, that's relatively prime. 10 and 7, those are relatively prime. But 4 and 10, no. 10 and 16, no, they're not relatively prime. See? So those are some properties regarding the GCD of more than 2 integers. But that's about it. And that's where I'm going to stop. And I don't know whether this thing, that GCD of more than 2 integers, will be necessary. I may write some exercise problems or homework problems on it, but that's going to be it. All right, so much for lesson 2. Thank you, everyone. And remember, here we went through 2 major theorems. Number 1, the division algorithm theorem. And number 2, Bezout's GCD theorem. Those 2 are major accomplishments that we did in lesson 2. Okay, all right. And as for section 4, yeah, all right. Maybe this is better. Yeah, that looks better.